Hello. So this is my demo for the Digital Logic Homework 4. This is the application I designed, and this is just the title screen for now, but the only inputs that we get here is just to press enter, and then we will get to see all the neat, fun, exciting stuff that I designed. So we can immediately see the chip box is what I've called it, as well as the navigation up here. The chip box just houses the different chip spawners, and as we can see from like the image themselves, they spawn the corresponding piece of logic. There is a bit more logic that isn't included in this demo. I think I have something like a manual press switch, a ground, but it's not necessarily anything super important. The important pieces that we can use are all present, and anything that isn't included we could design ourselves just by using any of this logic. Okay, so let's go ahead and select something basic. This is our power. The reason why these ones are surrounded by a dark outline is they aren't necessarily pieces of logic that we will use. They're more like user inputs or stuff that we would be expected to provide for our logic. So let's select our power. So we can see up here, this is our nifty little thing called our chip tip. It just explains what we have currently selected and what it does. So this says power, it's always 1. Now there is a couple of extra things we can do whenever we have a chip selected, and that is change the color. The logic behind this is 1, it looks really cool, and I mean, I could stop there, but the real reason why is because let's say you're doing something really complicated in here and you want to color code your chips just that way you can clearly see what you're doing. Let's say maybe you're trying to create something like an accumulator and you want to make sure that all the pieces that are related to the accumulator are all in one area. You don't have to like try and remember yourself. You can set those as a certain color. So let's set it to red. Now this node output is not related to the color. I'll show by changing it to yellow. This actually means that our output is live. So because it's power, it's always going to be red, but if we have something like, let's change it to an AND gate, and for fun, let's change it to a different color like blue, we can see that the output up here is green because it's currently not live. So let's change that. Now this turns yellow not because it is now live, this is our input, but because it's connected to something. And then we'll change that, and now we can see, boom, our output is now live. Let's take something like this light, change it to another, let's change it to green, since yellow and blue equal green. Alrighty. Now, as you can probably tell, there is a snapping effect whenever you get closer to the chips. This is just so that way whenever you're creating, longer logic, you can snap it easily, and it does not, however, take the nearest point between two chips, unfortunately. And it lasts, I think, like a second and a half, 3 seconds maybe, before it automatically goes away. So if you do want to place something like between these two, you can just wait it out, and then whenever it's done, you can just place it down here. Okay. So that is proof of our AND gate. Let's do something a bit more fun like our OR gate. Change that to maybe purple. And we'll take this, and as we can see, it's got a high output. Let's take our NOR gate. It's automatically high because we don't have either input, which means neither of these are live, which means that our output is high. But if we take something like this, it changes back to low, and if we do either input, it no longer displays. If we do want to delete objects, we can hold our left mouse button, pick them up, press right mouse button, and they disappear. Let's do our XOR gate. Let's do something a bit more interesting. This is what I call the sticky switch. There is a manual press switch, but it's not included in here because it's kind of difficult to work with. So sticky switch works fine. We can see that it's got a low output. That's because it's not pressed. So if we press it, it changes to a higher color. And now we can see it's got a live output. XOR gate. Looks like that works. It's got a high output. Let's do 2, and it turns off like expected. But let's give that a not gate, and let's connect it there. Oop. And as we can see, it's now high. And if we connected that to a light, it would shine like expected. Okay, let's move over here and do something else. Let's use our D flip-flop. Oops, let me move up here so we can see that chip tip a bit better. So the D flip-flop allows you to change whenever you've got it held. You can see the number of which flip-flop we're currently using. So right now it's just if the clock is 1, we set the input to the output. If we change that to 1 by pressing R, it changes it to edge triggered. And if we change it once more, it goes to falling edge triggered. And if we change it back, it goes back to 0. Let's give that a green. Okay. So it defaults with the first input, since it's got nothing in here, to off, and then Q0 to on, and here is our clock input. Since we're talking about clocks, let's go ahead and use our clock now. So our clock defaults to 0, which means that it reverses every X seconds, but it starts low. If we increase that once more, it goes to reverses every X seconds, but it starts high. If we change it to 2, it pulses every X seconds and it starts low. If we change it to 3, it pulses every X seconds, but it starts high. We can see to the right of it the amount of seconds that we have on the clock. If we press T, we can change the amount of time that it takes before it pulses or swaps. If we hit 10 seconds, it goes back to 0.5 seconds. There is a little catch with the pulse. Unfortunately, there is a limitation with this engine, or maybe my programming, and that is if the pulse isn't every frame, it's 6 frames. So this runs at 60 frames per second, so it's 6 frames. And the reason why is because occasionally the output node and the input nodes weren't able to communicate to each other. It wouldn't pick up the output of the clock, and it would go through lulls, essentially, where maybe 1, 2, 3 times in a row it wasn't able to get the output of the clock. So I increased the amount of time that it actually pulses, but it works for this demonstration. So we'll go ahead and we'll leave it pulses every X seconds, but it starts low. And let's change that to maybe something a bit bigger, like 5 seconds. And as you can see, it pulsed there. Let's change this to a switch. Turn that off. Okay. Connect that clock right here. And as expected, no change happened because this switch is off. Let's change that to a light. We'll change the light to something a little bit more obvious, maybe red. Put it through a NOT gate, just for fun. And it's on. So change that to on, and whenever it pulses, it'll flip the color of the light. Perfect. Let's turn that off. As expected, it changes back. All right, so let's change this to edge triggered, and to make it a bit more obvious, we're going to delete the clock and we're going to use a switch. So we've got this as off. Let's change that to on. Let's change this back to off, and we will connect our output over here. So like expected, because this is low, it's still on. Let's connect that to here. Okay. So whenever we hit this switch, it's going to reverse these positions. So it's going to go up to high because it is edge triggered, which means this is going to change this NOT gate to low, and it's going to turn the light off. Perfect. Let's change this to falling edge triggered. So this is on right now. This is off though, so whenever we turn this off, it's going to change the positions. Perfect. Let's pull out our mux gate for a little bit more fun. Actually, let's go ahead and move this down a bit so that way we can work in a more clean environment. Okay, so we got our mux ready. Let's connect this to a switch up here. Connect it once again to a different switch. Let's turn both of these off. Since none of these have any inputs, we can leave it as is. Let's give this a switch. Give this one a switch. Let's give this a OR gate. doing something a little bit more complex here. Let's give this a AND gate. Move that down a bit more. Okay. Let's say or. Let's give that this one. Let's go and. We'll go this one. Let's do NAND of this one, this one. And let's just say not of this one. These are in no particular order. I'm just selecting random gates here, and then we'll kind of talk through the logic. I guess now is a good time of any to discuss why you can move chips over the UI. The logic is you can't select another gate when your hands are full. This could be a toggleable option in the options if I were to implement it. But basically, if you place a chip down in the UI, it should persist under the UI. Currently, the UI draws beneath everything, just so that way whenever I was doing testing, I could verify that everything works. So we'll go ahead and connect that here. So we are at 0, 0. So if either of these switches are on, it should turn on and it should turn this light on. Perfect. Perfect and perfect. Okay, so let's talk about 0, 1. So if both of these switches need to be on, so it does not turn it on. It does not turn it on, but this does. Perfect. Let's go 0, 1. Okay. So what does this one do? Well, this one takes this switch and does the NOT and, does the NAND and perfect. So we turn this one on, it's still good. This one on, it's still good. Let's turn both of them on and it's no longer good. Let's do the last one. So it only takes in this switch, runs it through a NOT gate, and it's not on currently because our our switch is on. Turn that off and we're good to go. Let's do our decoder now. Okay, so since we are at 0, 0, currently the output 0 is on. Let's connect this to a switch. Let's connect this to a switch. Let's connect this. Actually, I'll do different colors. Why not? We'll do this one white. Unfortunately, with these bigger switches, the range of which you can snap to them can be somewhat irritating. That is definitely something I would change as a toggleable feature. Do that one. So we'll do 1 as white. We'll do 2 as red. We'll do 3 as blue. And we'll do 4 as purple. We'll do this switch as red. We'll do this switch as blue. Okay, so just to talk a little bit through the logic here, what I want to do is if neither of these switches are on, we will do white. If only the red one is on, we will do red. If only the blue one is on, we will do blue. And if both of them are on, they mix colors and it goes to purple. So let's do red. Oh, sorry, I got those mixed up. Okay, red. Perfect. Blue. Looking good. And we mix both of those colors. Awesome. All right, so we can scroll back over here and check out the different logic that we've got going on. And it's all still running as expected. I hope you enjoyed this demo. I'll include anything that I think I missed in this demo in my report. If there are any doubts or questions about anything I've shown today, I can definitely answer them, or I will happily provide the executable file, although I do intend to make some changes to this because I've quite enjoyed working on this project. Thank you so much for your time, and I hope you have a fantastic evening.